Good morning, all of you. In the previous class, we were discussing the previous year's questions. We'll continue that, and after that, we have to learn Van Hoff's factor. Van Hoff's factor. Okay, in 2011, again, Rawls' law in its general form, FORM. Henry's law about partial pressure of gas. Now, a solution prepared by dissolving this much mg of a gene fragment in 35 ml of water has an osmotic pressure 0.335 torricelli at 25 degrees Celsius. Assuming that the gene fragment is a non-electrolyte, calculate its molar mass. Here everything is given in different units. We know that the equation is pi v is equal to nbrt. What is pi? Pi is 0.3, I'm writing here 0.335 torricelli. If you that convert into atmosphere, then only you can take the R value in atmosphere, liter atmosphere per Kelvin per mole. So first we are converting this torricelli into atmosphere. So divide by 760 mmHg. So after dividing this 0.335 upon 760, we can write it as atmosphere into V is given in ml, so that is to be written in liters. So 35 upon 1000 liters is equal to NB, that is WB upon MB. What is WB? WB is given in 8.95 mg. So that you have to divide by 1000 to write in grams. So 8.95 upon 1000 grams into R value. Now you can take in liter atmosphere, that is 0.082 liter atmosphere per Kelvin per mole into temperature. Temperature is given in degrees Celsius. So 25 degrees Celsius means 298 Kelvin. So what you have to find out? You have to find out this MB. MB, where we will write MB, this is WB upon MB. WB upon MB. So MB you can calculate. MB's unit will be in grams per mole. Now, what all things will get cancelled? So atmosphere will get cancelled. Then liter will get cancelled. Then what all things? This K get cancelled. What all things remaining? Grams per mole. So MB you have to calculate. Its unit you should not write grams per mole during this calculation and cutting and all. That will be derived from this. After cutting and all, what will be remaining? That is coming as the unit of the molar mass. So MB you are calculating. MB's unit will be coming from this. After all cutting, what will remain? That is grams per mole. So here everything is given, but nothing is given in the proper term. everywhere you have to convert. The storically you have to convert, then volume ml you have to convert, degree Celsius you have to convert, and R value you have to take in liter atmosphere, since you are converting this torricelli into atmosphere. Suppose if it is in bar, then you will be taking here liter bar. So here it will be 0.083 liter bar. Next, this we have already done this. This is a repeated question. This is a repeated question. Then mole fraction ideal solution is a solution which obeys Raoult's law at entire range of concentration. Then azeotrope we have seen. Then osmotic pressure, the pressure applied on the solution side just to stop the flow of the solvent. Abnormal molecular mass, that we'll be seeing while learning Van Hoff's factor. Then Henry's law, boiling point elevation constant. What is boiling point elevation constant? We know that delta TB is equal to Kf dot m. So Kb dot m. This is Kb dot m. Kb dot m. So the question is, define this Kb, boiling point elevation constant. So you can define it as it is the delta TB. It is the elevation in boiling point when molality is unity. Similarly, you can define Kf also. It is a depression in freezing point when molality is unity. In that way, you have to make a definition. Or you can give the equation, give the expression and explain the terms. That also possible. Then this is a direct question. State Raoult's law. Okay, how does Raoult's law become a special case of Henry's law? How does this also be discussed? Then it's a direct question, no problem. Here again, a solution of glucose in water is labeled as 10% means 10% means you have to consider 100 gram of the solution. What would be the molality? What is molality? Molality small m is equal to number of moles of solute upon mass of solvent in kg. So solvent you have to separate from the solution. You are consider 10% means 100 gram solution you have to consider. 100 gram solution means this is 10%, that means 10 gram solute and 90 gram solvent. 90 gram solvent. So m is equal to that is molality, which is represented by small m, Wb, that is 10 upon, this is glucose, that is 180, whole divided by mass of solvent 90 upon 1000. This is the molality. So molality is the number of moles of solute upon mass of solvent in kg. Next, why are aquatic species more comfortable in cold water than in warm water? In warm water, the amount of dissolved oxygen will be less. So you have to explain in terms of KH value. As KH increases, solubility decreases. So you can say in warm water, KH of oxygen, KH of oxygen will be high. KH is higher, that's why solubility is lower. So you have to explain. You know that as temperature increases, solubility decreases. Not only that, you have to explain by means in terms of KH values. It means KH in high or low in that way. What happens when we place blood cells in saline water, that we have explained, and this one is again a direct question. And here, a solution containing 15 gram of urea, a solution containing 15 gram of urea, molar mass is given, per liter of the solution in water has the same osmotic pressure as a solution of glucose. Calculate the mass of glucose present in 1 liter of the solution. 1 liter of the solution. 15 gram of urea per liter of the solution. So, per liter means 1000 ml. 1000, so volume here 1000 ml, and that solution is having the same osmotic pressure as a solution of glucose in water. Once again, a solution containing 15 gram of urea, molar mass is given, per liter means 1000 ml of solution in water has the same osmotic pressure as a solution of glucose in water. Calculate the mass of glucose present in 1 liter of its solution. So osmotic pressure is the same. That means pi. Pi 1 is equal to pi 2. And that volume is also 1 liter, 1 liter. So that volume is same. So what remains, and R is the same. Temperature. Temperature same. Calculate the mass of glucose. A solution of 15 gram of urea per liter of the solution. Temperature, room temperature, both are in room temperature. So what is remaining here? That is WB upon MB in one case. Only this portion there is difference. So 15 gram of urea upon its molar mass 60 is equal to, then next WB, that is glucose WB, that is WB upon 180. So calculate the mass of glucose present in 1 liter of the solution. So both are 1000 ml, both the solutions are 1000 ml, means both have the same volume, same volume. So you can calculate WB. I'll explain by taking the equations. Pi is equal to, or okay, NB upon V. Pi V is equal to NBRT. So pi 1, here pi 2, both are same. Pi 1 and pi 2 both are same. They are telling osmotic, same osmotic pressure. So that side also, that is NB upon V RT. So here pi and pi both are same, both are same volume. So I'm equating these two equations, that is V same, R same, T same. So only difference is this NB1, I'm writing NB2. One is of urea and one is of glucose. So here NB1 is equal to NB2. Rest everything is same. The only difference is, means this thing is same as that of this thing. Why? Because they are telling pi and pi. Pi 1 and pi 2 both are same. So this I am equating with this. So in that R same, T same, V same, only difference. The difference is only in that number of moles. Number of moles. So here what is NB? NB, that is 15 gram of 15 gram of urea, that is Wb upon its molar mass is equal to, now calculate the mass of glucose, that is Wb upon 180. So you can find out Wb from this. Next question is what type of deviation shown by a mixture of ethanol and acetone? Positive deviation, reason you know. Then okay, the similar question, the same question what we have done here. Here only molality is asked, but here molarity is also asked. What is molarity? Molarity, that is number of moles of solute. Molarity, capital M is equal to number of moles of the solute upon volume of solution in liters. Volume of solution in liters. Now, here that is NB, a 10% solution. 10% solution means 10 upon 180. Now, volume of solution, previously we wrote 90 upon 1000 because there we needed mass of solvent in kg. Now mass of solvent, we know that 90 is the mass of the solvent. Now this is the mass of the solvent, but we need here volume of solution in liter. So density is given, so you convert that mass into volume. That we know that mass by volume is density. So volume we are calculating, that is mass by density. So 90 upon its density. Density is given here, see 1.2. So but what we are getting is in ml. That you have to convert that ml into liter by dividing this value or dividing this thing by 1000. So now it is in liters. So mass by volume, this mass by density, you got volume in ml, but we need in liters. So you are dividing that ml by 1000 to get in liters. Then you can apply in the equation molarity, capital M is equal to number of moles of solute upon volume of solution in liters. Then next question here comes Van Hoff's factor that we will learn after this class. Which colligative, write the colligative property which is used to find the molecular mass of macromolecules, of course osmotic pressure. In non-ideal solution, what type of deviation shows the formation of minimum boiling azeotrope? Minimum boiling azeotrope. So solutions which are having positive deviation, that means vapor pressure is high. Positive deviation, that means vapor pressure is high, that means minimum boiling point, that is called minimum boiling deviation. Then rest year's questions are the repeated questions. Only one is remaining, that is in Van Hoff's factor. That was in 2019. A question based on this Van Hoff's factor was asked, calculation that we will learn after learning this Van Hoff's factor. Now, we are moving to abnormal molar mass and Van Hoff's factor. Abnormal molar mass and Van Hoff's factor. Van Hoff's factor. A volatile solvent is taken down also. These molecules are there, and here we have the vapor pressure, and this, suppose if it is a solution, then vapor pressure will be less. This is the vapor pressure, this is the solution. Compared to the pure solvent's vapor pressure, it has got a vapor pressure, though it is less, it has got a vapor pressure. Now, first we are going to a solution in which the salt dissociates. When we put the salt or the solute, when we put the solute, you see in this case, suppose 3 are here. 3 solute molecules are present. That's why the vapor pressure decreased here. The decreased vapor pressure is shown here. Why? Because some of the surface area is covered. But suppose the solute is, each solute molecule is getting broken into 2. So this one is broken into 2. It is broken into 2. So you can consider that masoor dal, orange color dal, which get split, which gets split into 2. So what happens? This got split into 2. So I'm showing it as, see, 2. This got split into 2. Now this also got split into 2. Split into 2. Now this also got, means for example this is NaCl. One NaCl molecule gets split into Na plus and Cl minus. So what happened? Double the surface area is covered. Double the surface area is covered. So vapor pressure, the vapor pressure decreased. Vapor pressure decreased. Vapor pressure decreased. Vapor pressure halved. Vapor pressure is halved. Why? Because double the surface area is covered. Vapor pressure is halved. Now delta TB, that is change in that boiling point, that is doubled. So delta TB is doubled. Now, what is this delta TB? Delta TB is equal to KB dot WB upon MB into WA upon 1000. This is the equation what we have learned. So what happened here? Delta TB, delta TB, that is doubled. Delta TB is the difference. That is doubled. Now you see, if you are calculating the molar mass, you are calculating the molar mass. Here, double value of delta TB. So what happens? Molar mass, if you are calculating, that will be half. That will be halved. So are we getting actual molar mass? No. By this experiment, means we put this NaCl or we put this KCl, for example KCl. When we put this KCl and calculated, experimentally when we calculated, we are getting the molar mass as 37.25. You are getting this molar mass calculated 37.25. KCl. KCl solution. KCl is the solute added. Now, what is the actual molar mass KCl? You can calculate KCl's actual molar mass. That is 39.35.5. So 5, then 74. 74.5 is the actual molar mass. What we got is 37.25. This is actually half of this thing only. Experimental value, what we are getting is 37.25. We didn't know what happened. We got a shock. We expected 74.5. But when we did the experiment using WB and WA, using KB of this water and all, we got a shock that why this got halved. Why this got halved? Because surface area covered doubled, vapor pressure halved, delta TB doubled. The delta TB only what we got experimentally we applied in this equation, and we got this 37.25 in the case of KCl. So there is a difference, means the molar mass what we calculated is halved. So here, to make it correct, what we have to do to get this value, to get this value, to get this value or this value 74.5, we have to put something here. Means we have to multiply it by what factor? 2. This factor with which we multiply is called Van Hoff's factor. We have to multiply this by 2, then only we will be getting this molar mass properly. So what is this 2? 2 you can take it as number of particles obtained from each molecule. That is, from 1 KCl, how many particles are obtained? How many particles are obtained? That is 2 particles. So that is 1 particle, 1 particle, 2 particles. So that number we are putting here, we call it as Van Hoff's factor. Or generally, I can write delta TB. To get the correct value, I have to multiply, means I, that factor I am writing here, it is 2, here it is 2, that factor I am writing I kb dot m, I Kb dot m. So this is called Van Hoff's factor. So by putting this Van Hoff's factor, that depends upon the type of the solute, Here it is 2. Suppose if the solute is K2SO4, then how many particles will be coming? 3. So here I is equal to 3. The rest we will be continuing in the next class. Thank you.